Good evening, everybody. Welcome to another edition of Final Countdown. It is actually week number 7, but we'll be discussing, like I said earlier, all the day 4 papers for all the weeks given so far. So all the papers completed up to 2005 will be completed fully. Okay, right. Let's get into work. Read the following passage carefully and answer the questions given. Now remember, he is based on electric fields. Now, to properly do the calculation, we must make sure that, just like I always say, whenever there is a paragraph question, don't read the whole paragraph first. Make sure you go point by point. So, here, small idea. One important application of electric discharge in gases is called electrostatic precipitator. This device is used to remove particulate matter. So here they are telling you the reason why it's being used: to remove particulate matter, electrostatic precipitator from a combustion gases, thereby reducing air pollution. They are especially useful in coal power plants and in industrial plants that generate large amounts of smoke. Modern precipitators are able to eliminate more than 99% of air and dust by weight from the smoke. Figure shows the arrangement which gives a basic idea of an electrostatic precipitator. Here we go, electrostatic precipitator. So here, a conducting wire running down the center is maintained at high potential. So this wire here is maintained at very high potential. Relative to the ground, outer cylindrical conductor. Polluted gases enter at the bottom and pass through the electrostatic field. The strong electric field, now look very carefully. The strong electric field causes corona discharge around the wire, and the formation of positive ions electrons and negative ions such as O2. Positive ions electrons and negative ions such as O2 minus. As the electrons and negative ions are accelerated towards the outer wall, the impurity particles in the stream gas become large by collisions. So as the electrons and negative ions are accelerated towards the outer wall, the impurity particles in the stream gases become charged by collision and ion capture. Since these impurity particles become negatively charged, they are drawn to the outer wall. So outer wall is positively charged. Here, outer wall is positively charged. Where they stick, by periodically shaking and flashing the cylinder, the impurity particles fall loose and collect at the bottom. So you can shake the cylinder, all impurity particles fall down. Right. The phenomenon known as corona discharge is often observed near sharp points. Now when we did electric fields, near sharp points we drew out the electric fields. The charge particles are very high. Strong electric field occurs. So very high surface charge density. If the electric field intensity of the conductor is high enough, it can cause electrical discharge in air. So if it's more than this, guaranteed it cannot cause electrical discharge. This breakdown is initiated by molecular ions and electrons present in air, produced, for example, by cosmic rays. These ions and electrons accelerate rapidly towards the conductor under the action of electric field. On the way to the conductor, they collide with other molecules and thereby create more ions and electrons. Right. Now the question. What is the purpose have a look. Right. What is the purpose of using this device near coal power plants? So what's the reason? To reduce air pollution by collecting dust and particles which are there in the exhaust smokes in coal power plants. Right now. So the purpose of using this device is to reduce air pollution, removing dust and particles which are there in the exhaust gases which are there in coal power plants. Okay, right. Moving on. Do modern precipitators fulfill the purpose that you have mentioned? Justify your answer. Answer is yes. 99% of all modern precipitators, I remember saying 99%, yes. Yeah. Modern precipitators are able to eliminate more than 99% of ash and dust from the smoke. 99% of ash and dust can be removed. By modern precipitators. By modern precipitators. Is the wire maintained a positive or negative charge? Now, if you read this carefully, you will understand. As electrons and ions are accelerated towards the outer wall. Why is it accelerating towards the outer wall? Electrons are accelerating towards the outer wall. Because what? Outer wall should be positively charged or negatively charged? Outer wall should be positively charged. So outer wall is positively charged. Outer wall is positively charged. Electrons and ions will go. So what can you say about the charge on the main conductor here? He is going to be negatively charged. Very simple. Negatively charged. So moving on. So positive or negative? Negatively charged. Negatively charged. Very simple work. There, negative charge. What is the advantage of grounding the outer cylinder? So what's the advantage of grounding the outer cylinder? So you have learned this. So negative charges come. Excess negative charges. Excess negative charges can be what? Sent to the earth. Clear? So by grounding the outer surface, you are grounding the outer surface. Here electrons are collected. So by grounding it, we are stopping static electricity formation, or electric shock formation can be stopped. Right there. So by grounding the outer cylinder, by grounding, we can stop electric shock taking place. We can stop electric shock taking place. Okay. Therefore, for safety, we ground the cylinder. We ground the cylinder. So understood? No? Your home is also grounded for safety. Draw electrical lines of force in the vicinity of the wire. So I'll go back to the picture. I'll draw here. There you go. Electric field lines, positive to negative, perpendicular to the surface. Positive to negative, perpendicular to the surface. There you go, electric field lines. There you go, electric field lines. Okay. So these are cylinders, so radial electric field line, but 2D version is this. Right. These are there is a current between the wire and the outer wall. Is there a current between the wire and the outer wall when the precipitator is in operation? Explain your answer. Answer is yes. Electrons move. Electrons and negative charge ions move towards the cylinder. Move towards the cylinder. While positive charge particles will travel towards the wire. Where positive charge ions move towards the positive charge the negative charge center. Okay. So answer is yes, you have charges moving. If you have charges moving, that will be current. Why are the polluted gases sent in the bottom rather than from the top? Where? So many reasons. Number one, gases have low density. They easily rise up. Next one. If we send gas from the top, the gas will block the flow because it's trying to go up. Gas will block the continuous flow. Okay now? So gases are low density. It's naturally trying to go up. If you send from top, so it will just collect here, stopping the flow of gas. Proper ionization will occur. When sent from the bottom. So our main idea is we must ionize the particles coming. Dust and air particles coming. Okay? Dust and air particles coming. Right. Next one. If an O2 gas, if an O2 ion and an electron are at the same distance from the wire, which has the higher acceleration, give reasons for your answer. Now, very basic idea. Force equal mass into acceleration. Electric field into charge, mass into acceleration. Acceleration is EQ divided by N. Now, if you take O2 minus, right? O2 minus. Minus 1 means charge of electron. Charge is same. What about the mass? Mass of electron is smaller. So, mass of electron is smaller than mass of oxygen. Therefore, acceleration of electron is larger than acceleration of O2 minus. Like that. Both oxygen ion and electron have the same charge. have the same charge. But the mass of the electron is much more smaller. Mass of the electron is much more smaller. Correct? When the mass is smaller, the acceleration will be large. When the mass is smaller, the acceleration will be large. Okay? Right. State 2 methods whereby some molecules in air gets ionized naturally. Now, if you look at the paragraph, here ionization occurs due to corona discharge. So if you look at this carefully, so here, as electrons and negative ions, the strong electric field in the wire causes corona discharge around the wire and formation of positive ions, electrons and negative ions such as O2 minus. So corona discharge will ionize what? Corona discharge. So one method is corona discharge. Corona discharge. That is, the next is radioactive decay. Now due to radioactive decay, alpha decay, beta decay, gamma decay also what? Ionization will take place. Also, ions can be caused by friction or rubbing of surfaces. Okay, no? What's the next one? Method of induction. By induced charge. Okay, by induced charge. Right. If the magnitude of the potential of wire relative to the outer wall is V and the charge per unit length is lambda per cell, voltage is meant by lambda, by the following equation. So here you go, it's given by this equation. Calculate lambda. P is equal to phi 2 pi epsilon naught lambda. So 90 kilovolts 10 to the power 3 5 1 over 2 pi epsilon naught. 1 over 2 pi epsilon naught is given earlier. So you can see 18 10 to the power 9. 18 10 to the power 9. So 18 10 to the power 9 times lambda. Lambda is 90 10 to the power 3, 90 10 to the power 9, 10 to the power minus 6 coulomb per meter. 10 to the power minus 6 coulomb per meter. So you know, minus 6 coulomb per meter. Right. Next one. Assuming that the wire to be very long using Gauss theorem, show that the electric field intensity distance R is given by this equation. So wire is infinitely long. I hope you all remember Gauss theorem. Consider a cylindrical Gaussian surface. Cylindrical Gaussian surface. Remember the wire is negatively charged. Field lines are coming in perpendicular to the surface. Field lines are coming in perpendicular to the surface. At a distance simple r. Right. Look at the board carefully. Applying Gauss theorem, E times A equals sum of charges over epsilon naught. Field lines are coming into the Gaussian surface, so minus E times Gaussian surface area 2 pi r L. We will take this length as L. 2 pi r L. What's the total charge inside? Charge per length is given. lambda times L will give you the charge. Lambda times L. So lambda times L divided by epsilon naught. L will cancel off. And don't forget it's minus charge, negative charge. Minus minus cancel off. L will cancel off. Lambda divided by 2 pi epsilon naught R. Lambda divided by 2 pi epsilon naught R. There you go. That is your electric field using Gauss theory. So using Gauss theorem, easily you have found the answer. Right. Determine electric field distance R equal 1 millimeter. Show that the value is greater than the breakdown electric field. E is equal to 18 10 to the power 9. So what we do is do the substitution first correctly. Lambda 2 pi epsilon naught R 18 10 to the power 9. Lambda is 10 to the power minus 6. R is 1 millimeter. Simplify this carefully. 18 10 to the power 6 volt per meter or Newton per coulomb. 18 10 to the power 6 is greater than 18 10 to the power 6 Newton per coulomb is greater than 3 10 to the power 6 Newton per coulomb. Therefore, the electric field exceeds breakdown electric field. Exceeds breakdown electric field. Right. So exceeds breakdown electric field. Identify the quantities. Right. So here you go, you have found your answers. It exceeds the breakdown electric field. Right. So breakdown electric field is given here in this question. Breakdown electric field is given 3 10 to the power 6. The value here is 18 10 to the power 6 greater than the breakdown electric field. Okay, right. Next one. Thermal conductivity K is defined by the expression Q over T Ka theta 1 minus W over D. Right. What are they asking you? Identify the quantities Q over T. Oh, the rate of heat conduction. Rate of heat conduction through the conductor. Rate of heat conduction through the conductor. Rate of heat conduction through the conductor. Okay, no? Rate of heat conduction through the conductor. Right. What is theta 1 minus theta 2 divided by D? Temperature gradient. Right. State the conditions under which the expression is valid. So this expression is valid at steady state. Okay. Under steady state conditions and heat passes axially through the conductor. Right. Okay. Moving on. Suppose the average temperature of the surface. Of ice layer thickness 50 millimeter floating is minus 50 throughout the year. If ice layer continues to grow, the difference of temperature at the top and the bottom, find the time taken in hours to grow it by thickness 1 millimeter. Assume that the temperature at the water ice is 0 degrees Celsius. Yeah, right. Now, surface of an ice layer. Surface of an ice layer minus 50 degrees Celsius. Right. At the bottom of the Arctic Ocean, bottom is 0 degrees Celsius. Bottom is 0 degrees Celsius. So, assume that's the ice layer. What is happening? Heat is conducting axially. Heat conduction, axial. Thickness here is 50 meter. Find the time taken for the thickness to grow by 1 millimeter. I'll show that. Thickness here grows by 1 millimeter. That means with time the thickness here is changing. 1 millimeter. With time the thickness is changing. Right. So how can ice form? Water will give out heat and become ice. Absorb heat will melt. Give out heat and become ice. Right. Rate in which heat is transferred K times A. Theta 1 minus theta 2 divided by thickness D. Rate in which heat occurs. Look at this. M LF divided by T. K times area. Temperature gradient 0 minus minus 50. Thickness. Be careful of this thickness. Now here 50 and 151. Now the average thickness will keep on changing. There. Average thickness will keep on changing. So if you look at this carefully, these 50 and 1. So the thickness there is changing with time. Thickness there is changing with time. 50 plus. Initial the thickness was 50. Finally the thickness is 50.001 divided by 2. Average thickness. So what I am substituting here is average thickness. Why? With time the thickness is changing. Initial thickness is 50. Final thickness is 50 plus or 50.001. Average thickness is this divided by 2. Look at the board now. Most people won't consider this, but you must consider the average thickness. Right. What can you say about the mass? Area into thickness here 1 millimeter convert to meter into density of ice 900. That's the mass. LF is going to be 3.6 10 to the power 5. 3.6 10 to the power 5. 3.6 10 to the power 5. Time taken. Thermal conductivity is 2. Cross sectional area A. Temperature difference 50. What can you say about the average here? Now, with your experience, you can say something important here. Average 50 plus. If you look at it carefully, 50 plus 50.001 divided by 2. 50.0005. 50.0005. Average thickness. Looking at this calculation, basic work. Here you go. Area will cancel off. Area will cancel off. We can find the relationship for the time. Area will cancel off. You can find the relationship for the time. The time is going to be 1.6 10 to the power 5 seconds. Do they want in seconds or hours? in hours. In hours. So in hours how much? 1.6 10 to the power 5 divided by 3600. Divided by 3600. So approximately about 45 hours. Approximately about 45 hours. So if you do the simplification, here you can get the relationship. Right. So let's do the calculation. Simplify it. 900 10 to the power minus 3 multiplied by 3.6 10 to the power 5 50.0005 divided by 100. So 1.62 10 to the power 5. 1.62 10 to the power 5 divided by 3600, you will get 45 hours. You will get 45 hours. Yeah. 45 hours to grow 1 millimeter thickness. Huh? Right. Moving forward. Continuous growth of ice is however hampered by the presence of warm water currents. Right. That's why sea currents are very important. If sea currents are not there, ice layers will keep on growing. Warm sea currents will melt that ice. Here, melt that ice. Calculate the rate in which heat should be provided per unit area of the ice layer by such currents to stop the growth of the above mentioned ice layer at 50 millimeter. So we want to melt it. The rate of heat supplied. Rate of heat supplied by warm currents equals rate of heat absorbed to melt ice of 1 millimeter thickness. So MOT-LF, rate of heat supplied Q dot. Q dot equal mass is equal to area times 1 millimeter, density of ice 900, LF 3.6 10 to the power 5. 3.6 10 to the power 5. Divided by time. Divided by time. So they are asking you the rate of heat required. The rate of heat required so simple work, no? If you look at this carefully, why is ice layer formed? Because heat is flowing through. So I must supply heat at the same rate heat is flowing through. So if I supply heat at the same rate heat is flowing through, I can stop this ice layer forming. I can stop this ice layer forming. Okay. So here, very simple, you can represent the relationship. Very simple, you can represent the relationship. This part here, this part here, this part here is the same rate given here. Same rate given here. Which means the same answer is here. This part and this part is same. So this is your answer. So you can write 2 times A 50 divided by 50.0005. So Q dot per area 100 divided by so approximately 2 watt per meter square. 2 watt per meter square. Okay, now approximately 2 watt per meter square, because this answer is equal to that. So Q dot per area is this amount, right? If the warm currents provided heat at a rate of 0.5, so if I can supply 2 watt only, ice will not form. But if I am supplying less, what would be the thickness of the ice layer formed after 2 days? After 2 days. Right, now think. Here minus 50 degrees Celsius. Here 0 degrees Celsius. Think carefully. Rate in which heat is supplied here. Rate in which heat is passing through. Okay. So I am supplying hot water 0.5 watt per meter square. 0.5 watt per meter square. The rate of heat passing through per area is 2 watt per meter square. 2 watt per meter square. If I supply 2 watt, the ice won't be melting, the ice won't form. But I am sending less. I am sending less. Yeah. I am sending less means now there is an ice layer forming. Ice layer forming because of the difference between these two. Understand the concept? Huh? Here 2 watt per meter square is flowing through. If 2 watt per meter square came in, no ice will form. No ice will form. Why? Whatever comes in goes out here. Whatever comes in goes out here. Or whatever is going out forms ice, this is melting that. Whatever is required to form ice is being melted. Heat is passing through, ice is formed, this is melting. Heat is passing through, ice is formed, this is melting. Right. Now ice layer is there. Here 0 degrees Celsius, here minus 50 degrees Celsius. Heat flowing through is 2 watt per meter square. 2 watt per meter square. Will ice form? Yes. Ice is going to form. Ice is going to form. But I am sending only 0.5 watt per meter square. 0.5 watt per meter square. So if 2 watt came, it will completely melt. If 0.5 came, it can't completely melt. It can't completely melt. So the heat supplied by the net heat supply to melt ice, to melt the ice form, rate of heat per area given. Per area given. 0.5 watt per meter square. 0.5 watt per meter square. There. 0.5 watt per meter square. If 2 watt per meter square came, it will melt. Now only 0.5 watt per meter square is coming in. 0.5 watt per meter square is coming in. Right. So what's the remaining? What's the remaining? Thing and net. 2 watt came, 2 watt went. 2 watt came, 2 watt went. 0.5 came. Ice can't completely melt. Little bit of ice is melt. The remaining heat will pass through. What's the remaining heat? The remaining heat is 1.5. The remaining heat is 1.5. For 0.5 watt, ice is melted. The remaining heat is 1.5 watt per meter square. Right? So now there is a new thickness layer there. This is of course 50 meter. That's a different story. Here 2 watt came, 2 watt went. Ice is melted. 0.5 came. Thickness is maintained 2 watt. So 0.5 comes in, travels. Because of the difference here, 1.5 should go through. 1.5 should go through. So here no difference, 2 watt will go. With the difference now, here with the thickness increases, rate of heat supply will reduce. So here 1.5 will go. Here 1.5 will go. Right. Now they are asking the thickness form. They are asking the warm current spread for 2 days. Thickness of the ice layer forms. Look at the book. So you can calculate this. Very simple. You can calculate this. So we know the rate of heat supplied to form ice. We know the rate of heat supplied to form ice. Again look. Again I explain. 2 watt comes, 2 watt per meter goes. No ice is formed. 0.5 comes. But because of this difference, 2 watt should go. So 0.5 means the remaining is 1.5. There. The remaining here is 1.5. Thickness of the ice layer is formed there. 1.5. Right. So here, carefully look. Q dot K times A. 0 minus minus 50. 0 minus minus 50. Divided by the thickness there. So here you can say the average thickness 50 plus, initial is 50, with time is changing. 50 plus thickness, whole thing divided by 2. That is equal to, look at the word carefully. That is equal to ice formed. That is equal to ice formed. Ice formation M over T LF. M over T LF. Look at the word carefully. M over T LF. Right? M over T LF. Time is also given 2 days. Time is also given 2 days. So simplify this. Simplify this. So what I'll do is I will take the whiteboard out. So K times A, 0 minus minus 50, 50 plus thickness divided by 2, because thickness is changing with time. M over T times LF. Mass is area into the thickness. Area into the thickness is the volume. Volume into density. 3.6 10 to the power 5. 2 days. 1 hour is 3600, 24 times 2 days. So many seconds. So many seconds. Thermal conductivity of ice 2 watt per meter square. Right. 2 watt per meter square area 50 divided by 25 plus T divided by 2. Simplify this. Areas cancel off. Areas cancel off. Areas cancel off. So here you have 100. 50 plus thickness divided by 2. Simplify here. Thickness T. 900 times 1, 900 times 4. 4 times 1, 0.9. 4 times 1, 0.9. 0.9, 10 to the power 5. 48. 0.9, 10 to the power 5, 48. Right. Now cross multiply. Cross multiply. Here but you can solve it a different way as well. That will solve in a while. We take it like this. 4,800 9 times T 50 plus T divided by 2. 2 zeros cancel off. 6 times 8, 6 times 1, for 30 you have 6. 8 times 1, 8 times 20. 20T, 50 plus T over 2. Open brackets, 1000 T plus 10 T square. 1000 T plus 10 T square. 10 T square plus 1000 T minus 1 is 0. From here, thickness you can find. The added thickness you can find. So these are also a way to solve the problem. here 9.99 10 to the power minus 4. That's approximately 10 to the power minus 3. 0.001. Okay. So this is one way of representing it. 0.001 for the third decimal base. There is also another way to solve this. Look at this guy. Now we know the heat transfer. Rate of heat transfer. Rate of heat transferred is 1.5 watt per meter square. 1.5 watt per meter square. Okay. Per area. So heat transfer in 2 days 1.5. Now 1.5 watt per meter square is there. 2 days 3600 times 24. That is going to be joules per meter square. Joules per meter square. Connect this to ice formation. This is per area. 1.5 times 2, 3600 times 24. Mass, area times thickness, volume, 900, 3.6 10 to the power 5 divided by area. 1.5, 2 times 3600 times 24. Now, you can easily find the thickness. Let's see. 1.5 2 times 3624 divided by 900 3.6 10 to the power 5. So here you will get 8 10 to the power minus 4 meter. That's going to be 0.0008. So earlier one is also not wrong. For the third decimal place it's correct. But to be more specific here you can find it. So I'll explain this again. Look at this carefully. Look at this carefully. Now 2 watt per meter square is passing through, 2 watt per meter square is coming in, no ice is formed. If 0.5 watt per meter square passes through, 1.5 will go through this. So 1.5 watt per meter square, that will form ice. If I write the equation here, K times A difference, thickness form 50 plus T divided by 2, rate in which heat is passed per unit time. So time is 2 days. So what we did here was, for 2 days, we represent at the time. Now here you get a quadratic equation. For this quadratic equation, for the third decimal place, you get correct answer. Third decimal place, you get the correct answer. But be more specific. Rate of heat transfer is a second method. Method number 2. Method number 2. 1.5 watt per meter square is passing through. So I multiplied by the time, I get joules per meter square. So heat transferred when ice is formed per area That is that equation. Here also joules per meter square. Here also joules per meter square. Don't forget. Simplify the relationship. Thickness of ice form can be found. Thickness of ice form can be found. So again look at. So 0.5 is coming. 1.5 is passing through. Because of this 1.5 only this ice layer is formed. So directly what we can do is we can say 1.5 is passing through and then find the required basic answer. Okay, right. So this concludes week number 2, that's 2002 paper, day 4 work. Okay, day 4 work, which means we have done the electric field question and also we have done the thermal conduction question, thermal essay question in the paper, right? Okay. Next is the 2003 day 4 paper. 2003 day 4 paper. Right. 2003 day 4 paper. The first question is based on surface tension. The first question is based on surface tension. Read the question carefully. Right. 3 glass tubes are immersed partially in liquids ABC, in which the angles of contact are 30, 90 and 130. If the tubes are immersed vertically in the above cases, draw the liquid levels outside the tube. Okay. If the angle of contact is small, here you go. Liquid. You can draw the angle of contact, dot angle. This is your 30 degrees. Right. Next is 90 degrees. If the angle of contact is 90, liquids cannot rise. Angle of contact is 90, liquids cannot rise. So here, angle of contact. Here, angle of contact is 90. Next one, angle of contact 1/3. Angle of contact 1/3. 1/3 means like this. Here, angle of contact 1/3. Clearly indicate the surface tensions. So surface tension forces we can indicate in yellow. Here surface tension forces. Here surface tension forces. Here surface tension forces. Here surface tension forces. Okay, no? Right. Next, a glass tube of inner radius 0.5 mm is immersed vertically in a container of mercury, such that the lower end of the tube remains tensively below the surface of mercury. The tension, surface tension, density are given, and the angle of contact is 140. Acceleration due to gravity is also given. Derive an expression for the difference between the mercury levels of the tube and the container in terms of all these values. Right, look at the board now. Here, now the mercury level lower end of the tube remains 10 cm below. So derive an expression for the difference in height. So here you go. Derive an expression for the difference in height in terms of T, RT rho, T times G. Right. Look at the board carefully. Now, here PATM, here A, here B. That's outside C, that's also atmospheric. Right. If you look at this carefully, apply the pressure radiation. PATM plus H rho mercury G, that is equal to pressure at A. Also the pressure difference here, PB minus PC equal 2T over simple R. 2T over simple R. There. 2T over simple R. R is the radius of the bubble. R is the radius of the imaginary bubble. R is the radius of the imaginary bubble. Right. In terms of the radius of the tube. So look at this carefully. Radius of the bubble. So radius of the bubble, that is equal to R cos 40 is equal to simple R. R cos 40 is equal to simple R. So radius of the bubble is capital R. Here angle 40. Here radius of the tube. So if I show it to you all, like this, radius of the bubble. Here radius of the tube. Here angle of contact. Here angle of contact. Through the liquid is going to be 140. Here it's going to be 40. Here 50. Here 50. Because here it's 90. Now here tangent 50 here means 40 here. R cos 40 is simple R. Right. R cos 40 is simple R. Pressure at A is equal to pressure at B. Pressure at A is equal to pressure at B. So pressure at A is equal to pressure at B means put A here. Pressure at A minus pressure at C. 2T over. You show this in the board. Right. So here you go. There you go. PATM is here. X is here. A, B, C. Let me write the equations. Pressure at A is equal to PATM plus H rho mercury G. Also for the pressure difference here, PB minus PA equal to 2T over radius of bubble. PC, sorry. But all of you all know PA equals PB. Same level. Simplify. For PB you can substitute PATM plus H rho m mercury G. Pressure at C is equal to atmospheric pressure. That is equal to 2T over radius of the bubble. H rho m G. 2T over. All of you all know R cos 40 is equal to simple R. Simple R over cos 40. H rho mg 2t cos 4t divided over simple r. H equal 2t cos 4t divided by r rho mg. Now carefully substitute. Surface tension of mercury. Surface tension of mercury is given. 0.465. What is cos 40? Cos 40 is 0.766. Cos 40 0.766. Radius of the tube. Radius of the tube. Radius of the tube 0.5 millimeter. 0.5 millimeter. 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 Convert to meters. G is 10. Density of mercury. Density of mercury. 13,600. 13,600. From this you can get the answer for height. The answer height is 0.0105. 0.0105 meters. Right. So, how do you solve the capillary problems? Here PATM plus H rho G is pressure A. Pressure A equals pressure B, same level. It's bent downward, so pressure PB is larger. Excess pressure is PB minus PC. PB minus PC. PB minus PC. 2T over R. 2T over R. R is radius of bubble. R is radius of bubble. R radius of bubble. Simple R radius of tube. How do I get the radius of bubble to the radius of the tube? Radius of the bubble is R. R cos 40 simple R. Yeah? R cos 40 is equal to simple R. How do I know it's cos 40? Here angle of contact. This angle here is 140. This is 40. Vertical, horizontal 90. This is 50. This is tangent. 50 here means 40 here. So R cos 40 is simple R. R cos 40 is simple R. Okay. R cos 40 is simple R. Simplifying relationship, simple H can be found. Simple H can be found. So this is Roman 2 part A. Roman 2 part A. Roman 2 part A. Right. Now, part B. What must be the pressure of the air tube in order to form a hemispherical meniscus at the lower end of the tube? This also I have solved out. So now redraw it. Now redraw it. Now hemispherical meniscus at the bottom. Hemispherical meniscus means same radius as tube. Bottom of the tube is 10 centimeters. Bottom of the tube is 10 centimeters given in the question. So I won't turn it. I have the question with me. Bottom of the tube is 10 centimeters. Right? So, same as earlier. PATM plus H rho G is pressure. Outside pressure T. So this is connected to some maybe pressure pump. Here pressure is P. Here pressure is V. Here pressure is V. Look at the board channel. Right. What are they asking you? So radius of bubble equal radius of tube, you can write PATM plus H dash rho and G is equal to pressure at A. Pressure at A is equal to pressure at B. PC minus PB equal to 2T over radius of bubble. Remember, hemisphere forming means angle of contact is 0. When hemisphere forms, radius of bubble equal radius of tube. So PC minus PB 2T over simple R. Simplifies. PC is pressure inside. PB is PATM plus H dash rho and G. That is equal to 2T over simple R. P is equal PATM plus H dash rho and G plus 2T over simple R. Atmospheric pressure 10 to the power 5. 10 centimeter convert to meter, 13,600 into 10 plus 2 times surface tension over radius of tube. 10 to the power 5, 2 zeros cancel out. 13,600 plus 2 times surface tension 0.465 over radius is going to be radius of the tube is 0.5. Radius of the tube is going to be 0.5. Point 5 millimeters convert to meters. 0.5 millimeters convert to meters. Right. Now simplify this. You can find the answer. Simplify this, you can find the answer. Here 2.465 divided by 0.5 10 to the power minus 3. $13,600 here pressure inside 1.1546 10 to the power 5%. Pressure inside how? Right. Then what? Oil in a hot cup of soup floats in little air bubbles. Oil in hot cup, little air bubbles, oil bubbles. But when the soup cools, the oil will spread over the surface. Explain the above observation considering the surface tension of oil and water. What happens? When the temperature is high, the surface tension of water and oil are significantly different. So they don't mix. And there is no spreading. But when the temperature cools down, what happens? Surface tensions are almost similar, so what happens? Spreading of the oil layer will take place. So surface tension is the reason. If you make chicken curry at home, surface tension of oil is much more greater than water. So bubbles will form when it's very hot. But when the chicken curry is cool, check and see, oil is floating everywhere. That's because the surface tensions are approximately what? Same. So spreading will take place. Right there. When the soup is very hot, Surface tension of oil is greater than surface tension of water. Surface tension of oil is greater than surface tension of water. Surface tension of oil is greater than surface tension of water. Therefore, small oil bubbles will form. Therefore, small oil bubbles will form. But when the soup cools down, the surface tension of water and oil will approximately be the same. Surface tension of water and oil will approximately be the same. Therefore, oil will spread on water in the soup. Oil will spread on water in the soup. Right. So just a review back of that whole question back again. Now, why do you have a liquid meniscus form? Because of the cohesive and the adhesive forces. Here glass molecules are pulling the liquid molecules. The top surface is always in tension. The top surface is like pulled, like a rubber, like elastic. So we call it surface tension. If the angle of contact is acute, there is a capillary rise. If the angle of contact is obtuse, there is a capillary depression. Right? Now, in the next problem, here capillary depression takes place. PAPM plus H rho G is pressure at A, pressure at A equals pressure at B. Now pressure at B is larger, so the meniscus is bent upwards. PB larger than PC. PB minus PC is 2T over R. This is your excess pressure relationship. Excess pressure relationship. But PA equals PB. PC also open to atmosphere. Simplify this, we can find the capillary depression. Capillary depression. Next one is, I send in air into the tube. Sending air into the tube. Now a meniscus in the form of a hemisphere is formed at the bottom. Hemisphere means radius of bubble equal radius of tube. So radius of bubble equal radius of tube. Simple R equal capital R. So 2T over capital R, I can put simple R. The radius of bubble. Earlier we defined the term. Radius of bubble. Do the simplification. PAPM plus H rho G pressure at A, pressure at A equal pressure at B. PC minus PB is 2T over R. Simplify, you can find the pressure. Now when the soup is heated, why do you find oil bubbles? Oil has a higher surface tension, so they are close together. But when it cools down, oil surface tension and water surface tension are approximately the same. So what happened? Oil will spread along the soup. Okay, no? Oil will spread along the soup. Right. Okay. Right. Next is the thermal question in 2003 paper. Thermal essay question in 2003 paper. Right. A hollow closed tube of side 0.5 meter is made up of a thin metal sheet of specific heat capacity 200 joules per kilogram per Kelvin. A heating element of electric resistance 23 ohm. So here 23 ohm is there. And a heat capacity of 100 joules per Kelvin is placed inside the cube. So the heating element has a resistance of so much and a heat absorption of 100 joules per Kelvin. The cube is hung by an insulating thread at room temperature 27 degrees Celsius. A hollow closed tube of side 0.5 is made of thin metal sheets of specific heat capacity. These sheets are made from specific heat capacity here, 200 joules per kilogram per Kelvin. He is going to be hollow inside, hollow inside, right? Read. Assuming that the cube is filled with an ideal gas at atmospheric pressure and room temperature, find the number of gas moles in the cube. The atmospheric pressure and the R constant are given. neglect the volume of the heating element. Right. So let me apply PV equal nRT. Atmospheric pressure 10 to the power 5. Volume of the cube, each side is how much? 0.5 meter. Each side is how much? 0.5 meter, 0.5 cube. Number of moles 8.31. Temperature, room temperature. What's the room temperature? 27 degrees Celsius. Room temperature is 27 degrees Celsius, 300 Kelvin. Number of moles you can find. Let's simplify this. 10 to the power 5. 0.5 cube. Divided by 8.31 300. 5 moles. 5 moles of gas is inside. Okay, 5 moles. Right. Moving forward. The heating element which is connected to a supply 230 is switched on at T equal naught. At T equal 5 minutes, the temperature of the cube and the air inside reaches 177 Celsius. Assume that the heating element attains its operating temperature of 827 as soon as the switch is turned on. So quickly it reaches 827. During the 5 minutes, the total energy supplied by the power source. So energy supply V squared over R times T. 230 squared 23. Here we are talking about how many minutes? 5 minutes. That's 300 seconds. Simplify this. 230 squared divided by 23 multiplied by 300. You will get 6.9 10 to the power 5 joules. Amount of heat supplied 6.9 10 to the power 5 joules. Right. The energy absorbed by the walls of the cube and the heating element. Total mass of the walls of the cube is given 6 kilograms. Heat absorbed by walls plus heat absorbed by cooling element, by heating element. By heating element. That's your total heat absorbed. Total mass of the walls of the cubes are 6. MC delta theta 6. I think 2000, no? 200 joules per kilogram per Kelvin. Temperature change is given. So here 200, temperature change 177 minus 27. Heat absorbed by the heating coil. Heating coil heat capacity is given 100 joules per Kelvin. 100 joules per Kelvin. 100 joules per Kelvin. C theta 827 Celsius, no? So change in temperature there 827 minus 27 delta T. Simplify this. 6 multiplied by 200 multiplied by 177 minus 27 plus 100 multiplied by 800. Altogether 2.6 10 to the power 5 joules. 2.6 10 to the power 5 joules. 2.6 10 to the power 5 joules. Right? 2.6 10 to the power 5 joules. Right. The energy absorbed by the gas within the cube, the molar heat capacity is given. So delta Q, number of moles, molar heat capacity, delta T. 5 moles, 20 joule per mole per Kelvin. Temperature is 177 minus 27. 5 times 20 times 150. 1.5 10 to the power 4 joules. 1.5 10 to the power 4 joules. Simple work. Percentage heat loss from the system. So heat loss is heat given. Heat loss is heat given. Heat given we have found earlier. 6.9 10 to the power 5. Heat given minus heat absorbed. 6.9 10 to the power 5 minus. Here 1.5 10 to the power 4 by the gas. Then by the heating element separately you can find 2.6 10 to the power 5. Total 2.6 10 to the power 5. Let's find the heat loss. 6.9 10 to the power 5 minus 1.5 10 to the power 4. 2.6 10 to the power 5. 4.15 10 to the power 5 joules heat loss to the environment. So percentage heat loss is 4.15 10 to the power 5. Heat given 6.9 10 to the power 5 into 100. 6.9 10 to the power 5 into 100. Percentage loss is 60.14%. Percentage heat loss is 60.14%. Lot of heat is lost. Right. When the system reaches steady state, what do you mean by heat given equal heat loss? Find the temperature of the outer surface of the cube. Neglect the heat loss due to convection and conduction and assume that the room temperature remains unchanged. Stefan constant, right. What do you mean by steady state? What do you mean by steady state? Rate in which heat is given equal rate in which heat is lost. Rate in which heat is given equal rate in which heat is lost. Now, rate in which heat is lost to the surroundings is by what? Conduction. By radiation, sorry. Heat loss due to convection and conduction are neglected. Stefan constant is given, so guaranteed radiation is there. Radiation is there. So Q dot T equals EA sigma T to the power 4. Temperature of the outer surface. Temperature of the outer surface. EA sigma T to the power 4. But you have to be careful. Now, they have told you inside temperature is 177 Celsius. Outside temperature we don't know. So here rate in which heat is absorbed, is equal to rate in which heat is lost. Here is equal to rate in which heat is lost. Right? So from this you can build a very simple equation. So here temperature moving out, moving in, moving out. T2 to the power 4, T1 to the power 4. Net heat. Temperature inside, let's say T1. Temperature inside will take it as T1. Temperature inside T1. Temperature outside T2. So rate of heat loss is, simplify the relationship. Here the rate in which heat is supplied. So heat given is 6.9 10 to the power 5. In how many minutes? 5 minutes. So simplify this. 6.9 10 to the power 5. 5 minutes 300 seconds. E is 0.7. Surface area cube 6 sides. Each side is 0.5 square, 0.25. Sigma 5.67 10 to the power minus 8. Temperature outside T2 to the power 4. Inside 177 Celsius. No? 177 Celsius. 177 Celsius. So when the system has reached steady state, find the temperature of the outer surface of the cube, neglecting heat loss due to convection conduction, and assume that the room temperature remain unchanged. Room temperature remain unchanged. Right. So room temperature. So don't worry about this. Look at this carefully. Rate in which heat is given or absorbed by the container is given. Here outer surface T2, room temperature 27 Celsius. 27 Celsius are taken as T1. 300 to the power 4. 3 was theory of exchange. So rate in which heat is given is 6.9 10 to the power 5, 300 seconds. Simplify this, you can find the temperature T2. Outer surface temperature T2, room temperature 27. From this object point to the room it will absorb. So this is giving heat, this is absorbing heat. Net heat absorbed. Net heat absorbed by environment. So from the outer surface heat is given. From 27 it's absorbed. The net heat is the difference. Simplify this. 6.9 10 to the power 5 divided by 300 divided by 0.7 6 times 0.25 5.67 10 to the power minus 8 plus 300 to the power 4 465 Kelvin. 465 Kelvin. Here, 465 Kelvin. So I'll show this again. They are asking here outside temperature 27, outer temperature T2. From radiation there will be heat loss to the surroundings. So whatever produced here is lost. how much is absorbed to the environment. For T2 it's given from 27 it's absorbed. So difference in the fourth power of the absolute temperature. So that's the net heat absorbed by the environment. Net heat absorbed by the environment. 465 Kelvin. Clear? 465 Kelvin. Right? Okay. So that concludes 2003 A level day 4 papers. So today we have discussed 2002 A level day 4 papers, 2003 A level day 4 papers. So I'll see you again tomorrow with 2004 day 4 paper and 2005 day 4 paper. Keep working. Stay home safe.